Good afternoon. This is our narrated version of the PowerPoint for Chapter 9, and this is all about mid-latitude cyclones. Don't forget that cyclone refers to a low-pressure system. Okay, so, basically an area of low pressure. The cyclones tend to be circular. Don't forget that in the northern hemisphere, they are going to rotate in a counterclockwise fashion. So again, a cyclone is just simply a low pressure system. Another name for a cyclone, of course, that's what they refer to hurricanes in the Indian Ocean. So this chapter is all about a very special type of cyclone called a mid-latitude cyclone. And these things are going to form along the polar front. So if you were hopefully there in class with us today that we filled out the global wind patterns, remember about 60 degrees north latitude, you have a polar front, and that's where these mid-latitude cyclones are going to form, and they are moving across the United States from west to east all the time, bringing us lots of different weather patterns. So this, I believe, goes back to 1993. They may not be, oh, they are, yes, it is 1993. I actually remember the incredible snowfall that we had in Charleston, West Virginia during this time period back in 1993. Basically, it was a mid-latitude cyclone that brought a lot of snow into the Appalachians and New England. Good question here. As the global climate warms, will heavy snows be a thing of the past? And the answer is no. Okay, so global warming, well, these days we refer to it as climate change. That's a better term for that. It does not in any way mean that we will have less precipitation. We will have, if anything, more precipitation, because for every 1 degree Celsius temperature sea surface warming, for every 1 degree increase in sea surface temperature, you get up to 6% more evaporation. So the answer here is no. You will still have heavy snowfalls. Okay, so we're going to see with these mid-latitude cyclones that they are always going to have a warm front on the leading edge and a cold front on the trailing edge. We will discuss these fronts in detail in this particular chapter, and we will also briefly touch upon the stationary front, which, as the name implies, that's a front that's not really moving, it's stalled. We will also discuss an occluded front. The cold front moves faster than the warm front, so what happens to eventually cause the end of the lifespan of a mid-latitude cyclone is that the cold front catches up to the warm front, and we're going to call this an occluded front. And then we will briefly discuss dry lines as well towards the end of this unit. All right, so a warm front, it's going to be shown on our weather maps as a red line with red semicircles. And what happens here is that you have a warmer air mass moving in. It's going to overtake cooler or colder air. So the warm fronts have relatively gentle slopes. What do we mean by that? Well, we'll see that when we look at a 3D drawing of one of these. And as I mentioned on a previous slide, warm fronts move slower than cold fronts. In other words, cold fronts move faster than warm fronts. Okay, so these are pretty decent drawings. And here the two different drawings, they're showing a warm front advancing when you have stable air versus a warm front advancing when you have conditionally unstable air. We will simply focus on the top drawing there, a warm front with stable air. So when we say that they have a moderate angle, or they have a shallower slope, this is exactly what we're discussing. So for anybody that might have taken an earth science class before, this might look kind of like a thrust fault, which is a low angle fault, less than 45 degrees. So you have a shallow angle here to the approaching air system. Let's say that Pembroke is located there in the middle of the section covered with blue, with a cooler air mass over top. But you have warmer air moving in from the west. Okay, so that boundary is the front. It's shown there as the red line with semicircles. And what happens here, actually we discussed this briefly before when we were talking about lifting mechanisms, and this was called frontal wedging. So what happens here is that this cold wedge of air that's over top of Pembroke right now acts as an invisible mountain range, and the warm air comes in from the west and is pushed up and over the cold air. That warm air is going to cool adiabatically as it rises and expands, and that cooling will lead to condensation, cloud formation, and eventually precipitation. Generally, it's going to be mild to moderate precipitation. Okay, so east of the Rockies, these warm fronts are usually associated with maritime tropical air masses coming from the Gulf of Mexico. Back in Chapter 8, we talked about the air masses. So eventually you're going to end up with your nimbostratus clouds, which are those low, thick, gray clouds that cover the sky as far as you can see and bring light to moderate precipitation that might last for many hours or a couple of days. And just a reminder here on the top right corner of this slide, I think this was an extra credit question on maybe the first exam. Cirrus clouds approaching from the west are the first sign that you have a warm front approaching. We're going to leave this slide alone. We may come back to it later. We'll see. Well, okay, just one reminder. Why are they showing an egg beater here? Remember that in the United States, we are not producing any air masses because we have too much mixing. Instead, what happens is that the air masses are produced, well, really anywhere else around the United States, and then these different air masses move into the United States, and they are going to clash and create these mid-latitude cyclones, warm fronts, and cold fronts. So looking at this slide here, it will make sense when we get a little more into the cold fronts, and we mentioned that the cold fronts have a steep slope. Okay, so when your warm front is approaching from the west, remember that we live in a band of winds known as the westerlies, and our winds and most of our weather patterns are moving to us from the west. When that warm front's moving in, it has a shallow slope. When the cold front is moving in, it's going to have a much steeper slope, and you see that very well in this drawing. And that steeper slope is one of the reasons that we will end up likely producing those cumulonimbus clouds and thunderstorms when the cold front approaches. Okay, so we have seen these images before, but again, we will focus on the drawing on top, the one labeled A, a warm front with stable air. But something that we very briefly touched on back in, gosh, I don't remember what chapter, maybe chapter 5, when we were discussing types of precipitation, and we talked about the supercooled fluid. Remember that high up in the troposphere, like within a cumulonimbus cloud, you can have water that's very cold. It's a good bit lower than the freezing point, but it doesn't freeze. And in the winter time, you can end up with freezing rain or sleet. Either of those things can occur if you end up with this supercooled fluid coming down from the cloud and not refreezing on its way down and hitting cold surfaces and instantly creating a cover of ice. That is what we refer to as freezing rain or glaze. In the case, well, yeah, freezing rain or glaze. In the case of sleet, what happens is that supercooled fluid will end up melting into raindrops and then briefly refreezing into these tiny ice pellets before it hits the ground. Are we going to see any freezing rain or sleet this coming winter? Who knows? I kind of doubt it because this is a La Nina year. Okay, so I would recommend pausing this slide and just kind of taking a look here, reading through this chart, kind of giving you an idea of a warm front. So, and in particular, we're talking if you are south of the center of that low pressure system. I know it doesn't mention that here, but that's what they're referring to. And certainly we live far south enough that we're pretty much always to the south of the low pressure systems. People living, say, in Fargo, North Dakota, well, they might have some different experiences with the mid-latitude cyclones, warm fronts, and cold fronts because they are often north of the center of circulation. Okay, so cold fronts. Cold fronts, of course, this signifies that you have colder or cooler air moving into your area. And again, for us, this is always coming from the west. How's this going to be shown on a weather map? It's a blue line with triangles. And the slopes of the cold fronts are very steep. They're about twice as steep as the slope with a warm front. And we've seen that in a couple of 3D drawings already. So this steep slope allows for very fast uplift. So forceful uplifting of warm air in front. And remember, as this air is rising, it's going to expand and cool adiabatically. And as it cools, it's going to hit the dew point temperature and condensation will occur. Don't forget that condensation releases latent heat energy. So you end up with a lot of condensation droplets and a lot of latent heat energy being released. It means that that air mass is just always warmer than the air around it. So it's going to rise all the way until it gets up to the top of the troposphere. And what kind of clouds is this going to build? Well, this is going to build those cumulonimbus clouds that are, you know, very tall, have great vertical height to them. And of course, what is this going to bring you? Well, it's going to bring you thunderstorms. And when this happens along a cold front, it's very likely, depending on the time of year, that you might get supercell thunderstorms out of them. And cold fronts move faster than warm fronts, up to 50% faster than warm fronts, which is why the cold fronts eventually catch up with the warm fronts and make something called an occluded front. So this is a really nice 3D drawing here. Let's say that Pembroke is there in the middle of where you've got the warmer air in kind of the pink color. And so we're in the warm sector of the mid-latitude cyclone. The warm front has already passed over our area. But now you've got the cold front moving along, catching up and heading into our area from the west, and it's going to move pretty quickly. And again, you have a very steep slope, which you can see in this drawing, and you're going to have very fast uplift. You're going to have a lot of condensation and latent heat energy being released and allowing for that air mass to continue to be buoyant and to keep rising and rising, building that cumulonimbus cloud. And then, of course, you expect to get a thunderstorm from that. Now, the air that's moving in behind that front, remember that the front is that line, it's the boundary. The air mass moving in behind that front is going to be cooler or colder than what you had before, and that's going to be associated with more dense air that is sinking. So you'll notice to the left of our drawing there that you will have clearing conditions after the storm passes through. And in North America, our cold fronts are primarily formed when you have a continental polar air mass from Canada moving down into the United States and clashing with a maritime tropical air mass from the Gulf of Mexico. Here's another image showing the very steep approach, steep slope to that cold front. We might also kind of think of it as sort of undercutting that warm air and lifting it up very quickly. So just some images here to go along with what kind of weather do we expect to get with our cold fronts? Well, if you have any kind of warmth to the air that is rising, if you have any kind of instability, you should expect to get thunderstorms and cumulonimbus clouds. And if you look at that image there on the right, I'm guessing that's probably a baseball game, and notice all the splashing in the gutters up above the people's head there. So chances are, what is that? Yep, you guessed it, that is likely going to be hail. So here's another image of that table that we briefly looked at before. So I would recommend reading through this when you have time, and just you can always pause these narrated PowerPoints. Okay, so why do we get more severe weather, worse weather, more violent weather on our cold fronts than we do along the warm fronts? And it has to do with the steepness of that cold front. So the cold fronts are a lot steeper than the warm fronts. They also move very quickly. So the cold front is probably twice as steep as the warm front, and it's moving 50% faster than the warm front. So you're basically just going to get your very quick vertical displacement of air, meaning that you have lifting very fast. And again, as we mentioned previously, you're going to end up with a lot of condensation, latent heat, making that air mass buoyant. And as that air mass continues to rise and continues to cool and condensation continues to happen, that's how you end up with the cumulonimbus cloud, a cloud of great vertical thickness. And thunderstorms, potentially very severe thunderstorms. Okay, so this is a weather proverb. I don't know if this came from sailors. It's possible, or I guess it could have come from any number of people. Rain long foretold, long last. Short notice, soon past. Okay, so the first line, they're discussing warm fronts. So the warm front takes longer to move in, and there's a progression of clouds that you expect, which will begin with, of course, your cirrus clouds moving in from the west, your first indication that one of these low pressure systems is moving in. So it takes a while for that warm front to move in, so you maybe have a few days notice that you're going to get rain. And then when you do, it's going to be mild to moderate, and it could last for a day or two. And then the second line there, of course, is referring to cold front, short notice, soon past, saying that, you know, these cumulonimbus clouds and thunderstorms that roll in as the cold front is moving, well, they seem to build very quickly, so you don't have a lot of notice that is coming. I mean, you do if you're, you know, watching, you know, news or keeping an eye on your phone and actually paying attention to the weather. If you're just hanging out outside, then, you know, you don't get a whole lot of notice, and here is this thunderstorm, but it's going to move out pretty quickly because that cold front is going to move quickly. Okay, so just some clouds here to take a look at. Can you tell which one is a cumulonimbus? Well, that would be C, of course, in the bottom lower left. Okay, so this is a very generic but useful drawing of one of these mid-latitude cyclones. So it's a low pressure system. So the L is for low. It's red because it's associated with warm air, less dense air, rising air. Therefore, you get cloud cover. Okay, so remember that these systems tend to be circular. They're rotating counterclockwise. The winds are rotating counterclockwise in the northern hemisphere. You have a warm front on the leading edge, which you see here, and you have a cold front on the trailing edge, which you see here. And of course, the gray shading is showing where you would have cloud cover. So you have cloud cover there associated with the center of this low because it's warm rising air. And you have cloud cover at both fronts because both of those fronts are representing some kind of lifting mechanism. And what do you have in between? So in between there, you like say Louisiana, Mississippi, you have clearing conditions and warmer air than what's about to move in. Backdoor cold front is not on your exam, but this is a cold front that might hit, say, the northeast, and it approaches from the east or northeast instead of from the west, as we might expect. And these might also have a little something to do with nor'easters, which I believe we briefly talked about in a previous chapter. So we're going to skip this. We're going to skip this as well. Okay, what about a stationary front? So a stationary front, by the way, is going to be shown on the weather map. It's alternating blue and red, and you're going to have both the red circles and the blue triangles. So it's basically a battle between the warm air mass and the cold air mass. Okay, so this occurs when the airflow is neither toward the cold air mass nor towards the warm air mass. So the wind is going to be parallel to the line of the front, the stationary front, and this means that, at least for a while, temporarily, that front is stalled and it's not advancing. So you could say that neither the warm air mass nor the cold air mass are winning this battle, but eventually one of those air masses will overtake. So again, on the weather map, red semicircles pointing into the cold air, blue triangles pointing into the warm air, and this is going to be kind of alternating. And it can remain stationary for a while or moving very, very slowly. And these stalled fronts may remain over an area for quite a long time. And of course, it's possible that they might bring a lot of precipitation while they are stalled over your area. This is kind of a neat image here. If I were to ask you just roughly what season this might be, would you have guessed winter? Okay, very good. So what you see here is you see a warm, moist maritime tropical air mass moving up from the Gulf, heading into the United States and traveling east. But then you have cold air moving down from Canada, continental polar air moving down from Canada. And in between there, you have your stalled front. Now, what they have drawn north of the stalled front is the line of freezing. Well, we'll say that line is going to mark where you go above freezing to the south and below freezing to the north. So they might call that the 32-degree Fahrenheit line or the 0-degree Celsius line. And what do you have in front of that is rain. Well, they're specifically saying light drizzle here. But, I'm sorry, I should have said one in front of it. What to the south of it do you have? Now, what do you have to the north of that line? You are going to have freezing rain and then light snow. Okay, so is flooding possible with these stationary fronts? Absolutely. And might you get a good bit of freezing rain or snow with these stalled fronts, depending upon where you live, how far north you live, and what season it is? Absolutely. So if they won't stay stalled forever. They will eventually move, and they will either become a cold front or a warm front, depending upon which of those two air masses is going to win the battle and advance. Okay, this is another description here of a stationary front. You may pause and look at this if you would like to. Okay, the occluded front. This is fun. So the occluded front and stalled front are things we never have time to cover in the Earth Science class, just so you know. So for those of you that had that class in the past, this is new material here. So an occluded front, when you're rapidly moving cold air overtakes a warm front, an occluded front occurs. Another way, how I like to describe this, is the cold front catches up to the warm front, and that gives you an occluded front. So this is shown on your weather map by a purple line. I guess that's purple is what you would get if you took red paint and blue paint and mixed it together, and then you're going to have alternating semicircles and triangles. pointing in the direction of movement. And if you get precipitation along an occluded front, it's because this is a type of lifting mechanism. So this, I guess, would be just another form of frontal wedging or frontal lifting. So when the cold front catches up to the warm front, it's basically going to force the warm air in between up or aloft. If that sounds weird, like I don't know what you're talking about, we are going to have a drawing on an upcoming slide and it will make perfect sense at that point. Okay, so as part of this, so the occluded front, we can also refer to this simply as an occlusion, and a cold air wedges a warm air mass upwards. And then you end up forming a brand new front between the advancing cold air and the warm air that's being lifted. Hopefully our next slide is going to show that in a cross-section drawing. Okay, good. And this should show us step by step here over the next, say, 3 slides. So looking over there on the left, there's your typical mid-latitude cyclone. You see your cloud cover there in gray. You have cloud cover associated with the warm front on the leading edge, and you also have cloud cover associated with the cold front on the trailing edge. And then over on the right, that is a cross-section drawing of this. So, in front of the warm front, or to the east of the warm front, you have cooler air. You have the warm air mass coming behind it. It's going to be lifted up and over the cool air wedge. So that is a type of frontal wedging or frontal lifting. But the further north you are, the closer you're going to be to the occlusion. You're going to get to a point, like in this drawing, here from the side, you see that that cold front is pretty close to the warm front. There's not a whole lot of distance in between them. So that cold front moves faster than the warm front and is going to catch up to it. And of course, with both the warm front and the cold front here, you see the type of cloud pattern and weather we might expect to get. By the way, when an occluded front occurs, that is the beginning of the end of our mid-latitude cyclone. It's going to start to fizzle out at that point. Okay, so this is step 2 or time 2. We now have our warm front catching up to the cold front. So the map on the left, you see there that at the very top, you no longer have a warm front or a cold front. You now have that purple line with a semicircle and a triangle. That's your occluded front. And what does that look like? In a cross-section drawing, that's your image on the right. You now officially have the cold front having caught up to the warm front, and they're basically touching each other here. What's going to happen is that that warm air there in the middle where it says heavy rain, it's now kind of caught between two cooler air masses, and it's going to get forced upwards. And here you go. This is time 3 or step 3. We now see on that weather map on the left that the occluded front has gotten to be much longer. And then that image on the right, the cold front has absolutely overtaken the warm front. And now you have colder air moving in. It's now clashing with the cooler air, and the warm air that was in between is now forced aloft. And that, of course, is going to bring us some cloud cover and some light rain. But basically, this is the last stage in the life cycle of a mid-latitude cyclone. Now, this slide here is not on your exam, okay? But technically, there are 2 different types of occlusions. Okay, there is the cold type occluded front on the left there in diagram A. There is the warm type occluded front there on the right in diagram B. And the difference has to do with how cold or just cool the air mass is that's coming in from the left, overtaking the warm air. We are going to leave this alone for our first exam. We don't have time, even in a regular semester, to cover absolutely everything, and not everything has to be on our exam. You're certainly welcome to pause this recording and take a look at these things here. So The atmosphere is very complicated, and yeah, even our occluded fronts are going to have different types. Okay, the dry line. So the dry line is something we never have time to talk about in the earth science class, but we do always try to take time to talk about it in the weather and climate class. So a dry line is another type of boundary. It's technically not a front because it's not an intersection of two different air masses, but it's going to have to do with different dew point temperatures between a couple of different air masses. So you don't normally hear dry line here in the Carolinas or anywhere in the eastern United States where I have lived. I didn't even know about a dry line until I started studying this, because this is more likely to happen in the Midwest states. All right, so if they're going to develop, generally this is a warm weather phenomenon, so summer, maybe late spring, early fall, and they're going to form over the southern Great Plains. If we were having this class out in the Great Plains, you guys would have grown up hearing about the dry line, but it's kind of new to us. So this occurs when you have dry continental tropical air meeting moist maritime tropical air from the Gulf of Mexico. Okay, so think back to Chapter 8, the air masses, and remember that the continental tropical is hot and dry, and it's only going to appear basically in the summer, and it's going to form in Mexico and head up into the desert southwest of the United States. So you don't get dry lines all the time, only in the warm months. But the important point here is that you have a clash between continental tropical air, hot and dry, and maritime tropical, warm and moist, from the Gulf of Mexico. And remember that dry air is more dense than moist air. So that continental tropical air mass is going to undercut the maritime tropical air mass and kind of push it upwards. So this will be another type of lifting mechanism. Okay, so what happens here is that this can make a band of thunderstorms along a line extending, say, from Texas up to Nebraska that moves eastward across the Great Plains. And the reason it's called dry line is because you have much lower dew point temperatures to the west in that continental tropical air mass and higher dew point temperatures to the east in the maritime tropical air mass. So that very dry air of the continental tropical air mass is why this is called a dry line. It tends to be shown as a yellow arrow. Okay, here it is in yellow. I was wrong about the arrow. I draw it as an arrow on one of your exam questions. Anyway, so this is what the dry line looks like. And notice where it's forming. So this is over Texas. Kind of makes sense. So you have that continental tropical air that is formed in Mexico and moved up into, say, Arizona and New Mexico and is now moving east. And it's going to clash with the maritime tropical air moving in from the Gulf of Mexico. And it'll kind of situate in the middle, in between the warm front and the cold front of a mid-latitude cyclone. So it's shown in yellow, and it's going to have these open circles. And they're showing gray cumulonimbus clouds along the dry line because this is an area that you tend to get thunderstorms, and potentially violent thunderstorms, thunderstorms that could form tornadoes. Okay, so we will very briefly go through this material here regarding the formation of mid-latitude cyclones forming along the polar front, and then very briefly we'll talk about the life cycle of the mid-latitude cyclones. Okay, so just a little bit of review. Remember that the mid-latitude cyclones, they are big circular low-pressure systems. The winds are blowing or rotating counterclockwise here in the northern hemisphere. They travel from west to east in the westerlies. There's a warm front on the leading edge, a cold front on the trailing edge. They're rather big. Their diameters are going to cover many states at a time, exceeding 1,000 kilometers pretty easily. And yeah, you tend to get precipitation because you're likely to get precipitation along the warm front and along the cold front. So here again is our generic image of the mid-latitude cyclone. Notice how big these things are. I mean, it's kind of like a giant two-tailed comma sitting over the United States. And these things can span many, many states. They're very large. Remember, these are macroscopic. These were the smaller end of the macro scale. Macroscopic, really? I meant to say macro scale. These are macro scale winds. These are on the smaller half of the macro scale winds. And don't forget that the larger half of the macro scale winds included westerlies, trade winds, and easterlies. So this is a different way to show this image. Instead of showing the cloud cover, we're showing the precipitation. This is a good way to show it. And you see here that, yes, you should expect to get rain in the northern states there that are right there in the center of low pressure. You expect to get rain along the warm front, and then notice that you get heavier rain along the cold front. That's because we tend to have more violent weather and thunderstorms along a cold front, whereas along the warm front, we're just going to have mild to moderate rain. Okay, so you are not going to need to know about the formation of mid-latitude cyclones for your second exam. Let me say that now. So we will go through this pretty quickly, and we might skip some slides. Okay, so remember the polar front for the northern hemisphere. It's at roughly about 60 degrees north. And the mid-latitude cyclones tend to develop here along the polar fronts. So during the cooler months, the polar fronts are well-defined bands around the Earth. Anyway, basically what you have happening here is that you have colder air to the north colliding with warmer air to the south, and this is going to set up the formation of our mid-latitude cyclones. Okay, so the life cycle of a mid-latitude cyclone, this is not going to be on your exam, but we will just very quickly go through it anyway. So why is it going to form? Because you have a clash of two air masses along that polar front. So air masses of different temperatures and therefore different densities are going to move parallel to the polar front in opposite directions. Okay, kind of like movement along a strike-slip fault. Is movement parallel to that fault and in opposite directions. Now, under the right circumstances, this once linear boundary will become wave-shaped. And that's going to sort of set it on its path to becoming circular in nature. So eventually you're going to get that cyclonic flow, meaning counterclockwise or circular flow, warm air advancing poleward, forming a warm front, cold air moving southward, forming a cold front. Let's say that again. Warm air advancing north, forming a warm front, colder air moving south, forming a cold front. And you end up with low pressure there on the crest of the wave, and because of the Coriolis effect and the globe turning, the air begins its counterclockwise circulation. So in the mature stage of a mid-latitude cyclone, the pressure surrounding that low, or the L, is going to drop. Your winds are going to strengthen, and you're going to get that fully developed warm front and cold front and the associated weather. Now, once you start to have the cold front catching up to the warm front and you form an occluded front, that is the beginning of the end of our mid-latitude cyclone. Why? Because the cold air advances faster. It always does. Therefore, the cold front overtakes the warm front. We could think of it as the cold air mass overtaking the warm air mass. Your occluded front forms. So we'll very quickly move through a set of slides here, just kind of showing the life cycle of our mid-latitude cyclone. And on this slide, you've got all the 6 different steps superimposed here. I believe the next 6 or 7 slides are going to show each of these a little bit bigger. I'm going to very quickly click through these because this is not going to be on your exam. But as always, you are welcome to pause this recording and take a look at this. But in the top left there under A, you have your Air on either side of the polar front, moving in two different air masses, moving parallel in opposite directions. In step B, you're starting to form a wave, as in it just looks like a crest. That's why they refer to it as wave. In C, you're actually starting to differentiate the warm front from the cold front, and you're getting that counterclockwise cyclonic circulation going. And then the three at the bottom are showing, well, they're not really, I guess the mature stage is up there on the top at point C. All right, so we will quickly move through these slides. Notice as we go through these slides quickly that they're also including in these diagrams the movement of these mid-latitude cyclones from west to east. So they're going to form, say, in Canada or down here, you know, in the United States, but close to Canada. You basically need a clash of warmer air and cooler air to start the formation process of these mid-latitude cyclones. And look at the one on the very far right there. Look at all that purple. You have quite the occluded front going on, and that means that this mid-latitude cyclone is starting to fall apart. Okay, so in this slide here, we are looking at the cloud patterns associated with a mid-latitude cyclone. Now, I'm going to point out that, well, in this case, wow, they're showing us an air mass we don't see all the time on these maps. Not only are they showing us the maritime tropical and continental polar we expect to see, they're showing us the maritime polar affecting the northeast United States. Now, there are two cross sections here, E to A and then G to F. G to F we could leave alone because we don't live in those northern tier states. So we have no idea what life is like there. Maybe some of you have relatives there and you go and visit, but it's very different for them than it is for us here in the, say, southern 2/3 of the United States, where we are normally to the south of the center of low pressure. So if you look at that cross section down there on the bottom from E to A, and it's kind of showing you in the map as well the corresponding places, and you kind of see there your cloud progression. As the warm front is moving in, you go from your cirrus clouds to your cirrostratus, altostratus, and then eventually to your nimbostratus, rain clouds. So mild to moderate rain for at least a day, maybe a couple of days, and then you're going to have that warm sector of air that'll be relatively clear, maybe some cumulus clouds. But then that cold front is going to move into your area from the west, and you expect that to bring cumulonimbus clouds and thunderstorms. Okay, we are going to skip this slide here. We're going to skip this slide as well. As always, you are free to pause this recording and take a look at this. We're going to skip this slide as well. Skipping this slide as well. This is a neat image here. This is showing us a satellite image of one of these mid-latitude cyclones. Notice the center of circulation is pretty far north here on this one. It's right up there about the border of the United States and Canada, kind of right there, and I guess that is at Lake Superior that's in the top left there. And we might also say that in this particular mid-latitude cyclone, we already are seeing some occlusion. We're going to skip this. In your textbook, you can read about how remember talking about ridges and troughs? We very briefly covered ridges and troughs, maybe in chapter 6, I think it was. And ridges and troughs are going to correspond to highs and lows, but the ridges and troughs are at a higher elevation, like up high where the jet stream is. And there is some interaction here, a relationship between the surface cyclones and anticyclones that we deal with all the time, living here on our surface. There's a relationship between these surface cyclones and anticyclones and the ridges and troughs above. We are not going to cover that for our exam. That's not going to be on your exam. Okay, so you can stop here or pause and take a look at this. When we introduced cyclones and anticyclones back in chapter 6, remember that whatever you have at the surface, you're going to have the opposite higher up, aloft, as in, higher in the troposphere. So in a cyclone, remember that's low pressure, and you have higher pressure on the outside, so the winds are blowing towards the center of a cyclone. That is convergence. So with a cyclone, you have convergence at the surface and you have divergence aloft. So you have the opposite. And then in the case of an anticyclone, you have divergence at the surface because it's higher pressure in the center, so the winds are going to blow away from the center. So in your anticyclone, you have divergence at the surface, means you're going to have convergence aloft. And this is a decent drawing showing the interaction between, say, our surface anticyclones and a ridge aloft, and the interaction between our surface cyclones and a trough aloft. You do not need to know this for your exam. In general, most mid-latitude cyclones that are affecting us in the lower 48 states are forming along the polar front, but there are other places where mid-latitude cyclones can occasionally form. Here's a listing of them. I believe you will see this in a map format on the next slide. Indeed. So here you go. So the Pacific low and the Alberta low are going to be associated with that polar front, and that's where we expect most mid-latitude cyclones to form, but they can occasionally form in these other places like the Colorado low, the Panhandle low, that's Texas, the Gulf low, and the Hatteras low. But we are less likely to have our mid-latitude cyclones forming in these places. Are we going to skip this? No, we won't skip this. Okay. So mid-latitude cyclones, for the most part, they're traveling east across the United States, across North America. Why? Because we're in that band of winds known as the westerlies. So there are some exceptions, and the only one of these exceptions we'll take a look at is that last bullet there, nor'easters. So remember that winds are named for the direction from which they come. So nor'easters, that's referring to these low pressure centers, and the winds are blowing from the northeast. So these things occasionally affect New England, and sometimes even down into the middle Atlantic states. So, and nor'easters are low pressure centers, so they are basically mid-latitude cyclones as well. If you want to pause on the slide and read through this chart, you may do that. It's kind of giving you an idea of changes in wind direction, and does that mean that your pressure is rising or falling, and what kind of weather you might get with that. We're going to skip this slide. We're going to skip this slide. I think we're getting to the end of this. We're going to skip this slide as well. This is kind of neat. So it's just a reminder that, a lot of our mid-latitude cyclones are forming along the polar front, so they're going to be associated, with forming from the North Pacific, or up in Canada from the Alberta Clipper. But you do have the Colorado low that can occasionally form these, the Gulf low, and then the Hatteras low that occasionally can form these. But what you see here in common with any potential source of nor'easter is that they're going to track from west to east because we're in a band of winds known as the westerlies. We're not going to worry about steering. We're going to skip this slide. Now, can you occasionally get these high pressure systems, anticyclones, in the wintertime that dip very far south? And this is in conjunction with the polar jet stream dipping far south. Does that happen from time to time? Yes, indeed it does. We're going to skip this. It's not on your exam. We're going to skip this. We're going to skip this. Here we have a case study of a mid-latitude cyclone, and we are going to skip it. You may pause and look at this if you would like. Sorry, we're going to go back just to take a look at the occluded front beginning there. Notice that purple line up there. We're going to skip this slide. We may be about done with this unit. We're going to skip this slide. We're going to skip this slide as well. We're going to skip this slide. Nice solid image here of one of these mid-latitude cyclones.